Okay, we'll get going. It's an honor to have Anka Dragan here with us today. She's an assistant professor in EECS at UC Berkeley. She's been working on enabling robots to work with, I love this sentence, work with, around, and in support of people. She directs the Interact Lab, which focuses on algorithms for human-robot interaction that move beyond a robot's function in isolation, thinking more deeply about giving them the ability to generate behaviors that account for interaction and coordination with people. So it resonates deeply with Microsoft research directions and goals. The team in Interact Lab explores a number of different applications, including assistive robots, robots in manufacturing, autonomous cars, and so on. And these technologies build on interdisciplinary research, including optimal control, planning, estimation, learning, and insights that come from cognitive psychology. Anka, excuse me, everybody, it's Anka. Anka helped to found and serves on the steering committee for the Berkeley AI Research Lab, the Bear Lab. She's a co-PI of the Center for Human Compatible AI. She received a Sloan Fellowship, MIT TR35 honor, Okawa Award, and an NSF Career Award. And she, as many of you know, did her PhD work with colleagues here, in part, at CMU. So, Anka.
Thank you. Hi, everybody. Always great to be here. Thanks so much for having me. As Eric said, I tend to focus on the algorithms that are behind human-robot interaction. So I figured we'd start with just a couple of examples of what human-robot interaction looks like. So here's an example in work from collaboration with Claire Tomlin's group at UC Berkeley. We have a human labeled as human being for clarity. And we have this little quad rotor. And they need to navigate around each other and not bump into each other. That's all. And this, looks easy. But there's ways to screw even this up. So here's a way to screw it up. You make the wrong predictions about what's going to happen, and the quadrotor gets in the way of the person and even collides with the person. We want to avoid something like that. Here's another example. This is, imagine I have this robot, and it's doing some stuff for me, and it's right now moving this mug from one place to another. And as I see it move, I feel like it's keeping this mug too high up. So what do? Well, I want to be able to push on it, sort of correct it, right? To teach it to keep the mug closer to the table. The concern being that if it drops it, maybe it will break, and that's not good because it's my favorite mug, and so on. So also, a simple thing, ways that the robot can screw this up again. One way that it can screw this up is by not actually being compliant to my input and rejecting this external torque that I'm applying as a disturbance. That's an obvious way. A more subtle way is that, okay, maybe it's compliant like it was just now, but the moment I let go, it goes back to doing the task in the exact same way it knows how to do the task before. So I kind of have to keep pushing on it. It keeps coming back, and I keep pushing on it, and it feels stubborn. So we want to avoid also something like that. These things would be easy if a person were in the space of a robot. We can navigate around each other. If you push me, I sort of get what that means. But these human behaviors are tricky for robots to interpret. So because we haven't really given robots a manual for how to interpret our behaviors, right? We haven't written a human behavior for dummies manual yet. And in a sense, that's what a lot of my work is about, is providing such an instruction manual for robots. Now, formally, what happens when you have a robotics problem is you usually define some utility function, and the robot's job is to find a policy by R that maps states to actions that maximize the expected utility. That's kind of the definition of the AI problem. We've made some progress towards that. The challenge, what's challenging and exciting at the same time about interaction is that the moment the robot needs to do this in the same space as a person is also acting, the problem fundamentally changes at its core. And it changes because, at the very least, now the robot's utility is no longer just a function of the robot's policy. It also depends on the person's policy and how well these two policies end up meshing together. At the very least, because we don't want the human and the robot to end up bumping into each other, and usually because we want them to collaborate well and coordinate well and so on. And so for the robot to be deciding on what's a good idea, what's a good policy or trajectory for itself, it needs to start reasoning about the human, what they might be doing. And this is a pretty tall order, right? You need a model of human behavior. And so this is naturally something that we're going to want to involve data with. The question is, though, how? What's the right way to involve data here? In this kind of day and age, if I were to look at this problem, what naturally would come to mind is this approach of let's collect a bunch of data of people acting and fit some sort of black box policy to this data. So take a high capacity neural network and fit it to what we observe humans doing. And this is appealing for its simplicity, but unfortunately, it's not always going to work out. And the reason is, imagine that, let's draw on this slide, all possible policies. Only some of those are policies that a real human would ever take. The challenge is we have no idea where these are in the space of all policies. And so the black box approach to the problem is to cast a very wide net, is to use some class of models, high capacity models, and cover our bases. And that sounds appealing because it gives us a lot of flexibility. But what happens is we end up collecting some amount of data, even a large amount of data, and there are going to be a lot of policies in our hypothesis space that are consistent with this data that we collected. And so then what can happen is if we encounter any kind of distributional shift, we can be in trouble because chances are we haven't landed by magic on the one that happens to be the correct one. And so indeed what can happen if we plot the robot cumulative reward as a function of the amount of human data we expose the robot to is in some cases we might see that we don't get that much better with the amount of human data if the data doesn't come from the right distribution. And if we get on-policy data, well, that's really helpful, but on-policy data can be really expensive. Imagine for a human-robot interaction, that means you have a robot that's still learning, and it takes actions and see how people are reacting to that. And that's not something that you can afford to do in a lot of applications, especially safety-critical applications. And so then the challenge becomes, what hypothesis space should we be using? What is the space that we should be searching for a policy over when we're fitting a model of human behavior? In other words, what is the right inductive bias to use when it comes to learning for human-robot interaction? And that's really what this talk is about. And that's a question that has consumed me for the past few years. And I don't think I know the answer. I think I got a little bit closer to the answer. And so let me share some of the things that I found out with you today. So to start answering this question, what we have to think about is, well, if it's not arbitrary black box policies, what makes the human behavior, what makes us think that humans are not arbitrary? And to me, the key here is that we take actions not arbitrarily because the actions that we take are driven by purposeful decisions that we make. Now, we have this thing that we use to make decisions, and these decisions are in support of the stuff we want to achieve, of the intentions that we have, right? I'm walking this way because I want to go to the exit. I am steering this way on my drive home and pressing the acceleration pedal this way because I want to get home. And I want to stay on the road, and I want to not crash into things, and I want to be efficient, and I want to be comfortable, and so on. That's what I mean by intentions. And so it seemed to me that it's this notion of people are people, they behave in the way they do because of their intentions, seemed to me like this notion was something that we really ought to leverage when it comes to learning in human-robot interaction. But the challenge is that humans have intent is a very fuzzy statement to make. And so how do you take this and turn it into some formal, useful inductive bias for a robot to use? So that's kind of the journey that I went on. And I drew it here as this nice stroll downhill, but it was this kind of treacherous adventure. And then we'll get to dig our heels in a little bit today. So let me start with the starting point. So the starting point for me was almost like a 180 from the notion of black box policy. And it wasn't the answer, it wasn't the final answer, but it was a key component of the final answer. And that was, I didn't know when I thought about intent, I really couldn't figure out how to formalize intent other than to go back to essentially economics and say, intent corresponds to some utility, some objective function that the person cares about optimizing. There's something that they want. And I'm going to capture that via utility function. And in this talk, the utility function is going to be parameterized by some parameters that we're going to call theta h. Concretely, what does this mean? Well, let me share a couple examples. In this example where a person is navigating, theta h their intention might represent the actual goal location. The robot doesn't know the goal location necessarily, but it knows that it's one of some possible locations in a room. And it knows that the person will try to get close to their goal, will also try to be efficient, will try to avoid obstacles. When the person is driving a car, a vehicle, we know that they care about a bunch of things. Let's call these criterion phi. And what we don't know, so these are things like efficiency and comfort and safety risk and stuff like that. Now, I don't know how people combine these criteria. So maybe I'm going to call the trade-offs that they make, I'm going to use that to denote my theta h, and that's going to be the thing that the robot doesn't know about. More generally, you could think of theta h as being weights in some neural network that maps state and action to a scalar value for how good that is. You just have to be a little bit careful with that, because the whole point here is that the space of intentions, the space of theta h's, is supposed to be smaller than the space of all possible behaviors. And so that's the key, right? So when we go into this one, we have to be a little bit careful about what additional assumptions we make and how we regularize this. And again, the idea is that if I know theta h, that's really all I need to know. The theta h should induce the behavior so that I don't have to learn the behavior. I just focus on learning the theta h. Now, how does theta h induce behavior? So again, theta h corresponds to a utility. All that we really want to assume is that people are going to roughly be optimizing this utility. And I don't want to assume anything else. So the way I can formalize this is I can search for a policy that has maximum entropy. So I don't want to put any other inductive bias into the system, but subject to the constraint that in expectation, the value according to theta h should be roughly epsilon optimal, should be close to the optimal value. Yeah, question over there.
Implicit in the previous graphic seems to be that the human is seeing the same state x as the robot too, and I'm wondering why that is a legit thing to do. Maybe each human has a different perspective, right?
That's right. That's absolutely right. So something that we're not going to get at in this talk at all, but something that my group does work a little bit on, is this notion that we have different knowledge and different really beliefs about the world. And even that the person the person doesn't know everything the robot knows, especially the person doesn't know how the robot works. Something that we play a lot with is, okay, there's some parameters that are actually on the human side. There's a theta r, right, that the human thinks of as kind of hidden. And now how can the robot act in a way that is informative about these parameters that are hidden to the person? How can the robot act to expose those parameters? But we're not going to talk about that today. For this talk, we're going to assume that one, we know the physical state. The other thing we're going to assume for most of this talk is that the robot actually knows the dynamic. Both the robot and the human know the dynamics of the world. There's going to be an exception to this, but for the most part, we're going to assume that dealing with the physical world is solved. Why? Because that's hard enough, right? So we don't want to deal with that in humans, so it's sort of a divide and conquer. But thank you for that. That's a really important observation, an assumption that we're making here. So where was I? Okay, so we take this notion, we went from humans have intent to there's a utility function, and now we try to turn that into an actual behavior, an actual policy. And if you solve this, what you get is a Boltzmann distribution where essentially you expect the person to be taking actions with the probability that it gets exponentially higher when the when that action is closer to optimal. So that's the sort of the noisy rationale. We're assuming that people are kind of rational, noisy rational, approximately rational. So this then leads to you have a probability distribution over what might happen next that now your robot can actually use as its model. And again, the trick is that we don't learn all of that. We don't learn the whole policy. We just learn theta h. And the way we learn theta h is every time the person acts, so I took this step. Now this is an action that I took. The robot conveniently has this probability distribution that tells it how likely or unlikely that action is for any candidate theta h. So at least mathematically, computational are more difficult, but mathematically you can run Bayesian inference on this. You can do a Bayesian belief update to update your distribution over what this theta h might be. And you can do this online or you can do this offline. Yeah.
Yeah, so clarification question about that. So are we assuming that this behavior is happening with the robot in the system? And if so, do we have to worry about the human also simultaneously adapting to the robot?
I'll get there too. Hold on that question for 4 minutes or so, maybe. Okay, thank you. So you can do this offline too. You can collect a bunch of data of humans reaching their goals, avoiding obstacles, et cetera, and fit a model to that. And this is what we do with the quadrotors. So here's an overhead view on the right. We have the human and the quadrotor. They each have their goal. And what you'll see is the robot making predictions about what will happen at the next time steps. There's some low probability areas. There's some high probability areas. And now the quadrotor uses that to make sure it's not in the way, to make sure it avoids collisions with the person. Here's another example. The person first goes towards that goal. And you see it's not perfect, right? Because people are noisy when they're actually walking through the room. And so it's not like we get this perfect data. But we can make predictions about what's going to happen next and make sure that the robot can follow along. Now, this is one example. What I really appreciate, before I tell you all everything that's wrong with this, and I complain a lot about how it's all not right, let me at least share the things that I do like about this and what we've been able to do based on it. So in this particular context, we were looking at the actual actions that people were taking and treating them as observations, as evidence about their underlying intentions. And so basically what we were saying is that roughly speaking, and this is not a hard constraint, but roughly speaking, the action that we see the person take when it comes to their actual ground truth utility, that should be a better action to take than any other action that the person could have taken, which is why if you look at this equation again, it normalizes, this probability distribution normalizes over the space of possible actions that the person could have taken. Now, what's nice is that you can very easily generalize, instantiate the same formalism over a plethora of other kinds of channels of communication that the person could be giving you. For instance, if a person says, doesn't give you a demonstration, but gives you a comparison, says, I prefer this to that, right? Well, some very similar thing you can do where you can say, well, the probability of this is still proportional to the exponent of the Q value of that action, except that now the person hasn't looked at all possible actions and decided on the correct one. Now the person has looked at two options and decided which one is better. So we're only going to normalize over those two. If the person gives you a correction, like I was doing to the robot when I applied that external torque, Well, it's not that that itself is the right thing to do, but that combined with what the robot was doing, that combined action is something that we now know is good, so we can interpret it in the same framework. If the person tells you to stop, sometimes people say that. They watch the robot do something and they say, stop doing that. You'd think that there's not so much information in that. It's a very small signal, but actually it tells you quite a lot. It tells you that stopping, which I denote here by U0, doing nothing, even that is better than whatever you're actually doing. And believe it or not, we've gone as crazy as to also integrate into this framework observations of the kind, an actual reward function that a designer wrote down, engineered, but only for some particular set of situations. We interpret that as evidence about what they actually want in general. We look at the current state of the world, and we don't see an action, we just see a state. But there's only some actions, there's only some reward functions that are actually consistent to people having acted in the world and having now that state look the way it actually does, right? So if an example I can give you is you look at the world and vases are not cracked on the floor, and you can infer that chances are that people don't like to run over vases just because they're in the way. They would actually avoid them. Otherwise, you'd see more vases cracked on the floor. And so there's a lot of different channels of information that you could look at, and all of them are evidence about what people actually want, either that what they want to do or what they want the robot to do. So this is what helped us in this case as well, where now I push in the same way, and lo and behold, the robot takes it as information about how I want it to do the task, and it actually frickin' stays closer to the table. Just the simple wins with these robots. And so I like this. I like it because it's almost a unified formalism for actually accounting for different kinds of behavior that you see in humans. And taking that in and getting robots to be better at doing what we actually want and getting robots to be better at coordinating with us. Now the bad. We had some people play Lunar Lander, which is this Atari game. You look at these and, noisy rational doesn't really come to mind. It's more noisy than rational. The goal is to land, not crash, land between the two flags. And people don't do a great job at this. And so this is kind of one of the many examples where noisy rationality is just wrong. It's just that's not how people work. So what's going on there? In general, I'd say that by going to noisy rationality, we go from a very large space of policies to considering a very small space of policies. So we go for something that's perhaps too large to something that's perhaps too small. It's not flexible enough. It's too rigid. And so with noisy rationality, with all the successes we've been able to extract out of it, I felt a little closer to the truth, but it was clear that it wasn't the end of the journey. It was more like the beginning. And what's really, a way to look at this is honestly that what we do with noisy rationality is we take people, we get our special lens, we stare at them and squint through this lens until they start looking a lot like robots. And we just treat people as if they're robots left and right, and that's what noisy rationality is. Because if I take this equation and I sort of flatten on this slide, what you have is reward parameters go in. The world has some dynamic, some transition function. So that goes in, we plan, that gives us a Q function, optimal Q value function. And then the only difference between that noisy rationality and robot is that for a robot, state goes in and you actually do the argmax, take the optimal action. For a human, we're saying, oh, okay, they can be a little bit noisy. So we're essentially squinting and pretending like the person is a robot, which does not seem quite right. Now, what I decided to do is lean into this. So yes, it's a problem that makes noisy rationality too rigid, the fact that we're treating people as robots. But here's an interesting question. What if it's also the key to fixing it? In other words, what if we thought about when robots are not rational? Because the idea is it's almost like a recipe for fixing noisy rationality. The idea is that if there's ways in which robots deviate from rationality, it's probably because being rational is a hard thing to do. And if it's hard for a robot, that's in some cases it might be hard for a person too. And let me share an example of this. So one way in which it becomes hard for robots to be rational is that they don't actually know the way the world works. They don't have access beautifully to this dynamics model. And so if they don't, well, they have to do reinforcement learning. Their actions are not going to look noisy rational according to this definition when they're learning, because they're still going to be learning. So if you look back at lunar lander and people crashing all over the place, here's an overhead view of their trajectories. Red is failure, green is success. And then if you actually play with the dynamics model, with the way the world works, with the thrusters and the gravity and so on, all of a sudden their trajectories start making a hell lot of sense. And so the hypothesis here was that maybe noisy rationality makes sense, but maybe it's not for the correct dynamics model, because people don't necessarily know how the world actually works. Maybe they are being noisy rational, but under a different model, under some eta that we just don't have access to. And so naturally what we thought of doing is now making that as part of our inference. We don't just infer their intent, we also try to infer what it is that they're assuming about how the world works. It's hard to do this jointly. There's a lot of ambiguity between the two. And so what we actually do in practice is we collect these calibration tasks where we actually know what people are trying to achieve, or we can tell in hindsight, and then we fit dynamics parameters to that. And so far in this talk, I wrote down Bayes' rule, which is my favorite thing to write down, and sort of pretended like we can just do this, right? Here's an observation model, Bayes' rule it, done. Mathematically makes a lot of sense. Now let me tell you a little bit of the dirty laundry. It'd be very nice to do pure Bayesian inference. We don't afford it very often. Sometimes we do sampling. What we did in this particular case is we actually just computed the maximum likelihood estimate. So what is the dynamics parameters that best explain the human actions? And even that is hard, because to do this optimization, you have to differentiate through the Q-value function. And so that's challenging. And so the next little bit of dirty laundry was actually that we came up with this algorithm where we put the Q function itself which was representative as a neural net with weights W, as a variable that we're doing optimization over. And our objective now became twofold. It was about making the two sides of this Q function consistent. On the one hand, we wanted to find a Q function and dynamics eta that explain the demonstrations, right? So that give high probability. So the Q function has to explain UH. On the other hand, we wanted to make sure that the Q function is consistent with the left-hand side. It's consistent with the dynamics and with the reward. And there's an easy way to do this. You just have to make sure that the Q function essentially achieves low Bellman residual over some sample states. So you look over sample states for what your Q function currently is, and what it would be if you did one Bellman update. And that was it. So now what do we do with our inferred parameters? So we solved that optimization problem, and now we're online. The person is operating this lunar lander, and they're giving us some control command UH. Now, if we actually execute UH, we saw what happens. People crash all over the place. So this takes us to some state through the actual dynamics of the real world that is an undesirable state a lot of the time. So we don't do that. What we do instead is we take UH, and we pass it through forward dynamics according to what we inferred is how they think the world works. So this is essentially asking, where does the person think they're going to go if we execute UH? That's the dynamics model that we learned. And so that's a nice next state. And then we invert through the real dynamics we invert this, this state to get to the control that we need to apply to get there. And we apply that control instead. And it's not that it's perfect, but people don't fly all over the place anymore and actually land the thing when we do this. That was a struggle, but eventually we got there. So,
does this accelerate their ability to land the aircraft without assistance? So the information you're providing back doesn't help them learn how to land?
No. Well, we're not really providing, in this work, at least, we're not providing back any information. We're saying, and we could, and I don't know how to do that right, but it's a really interesting question. What we're doing here is taking the input that they're giving us and saying, I'm not going to execute that. I'm going to try to execute an input that leads the craft to the state that we think that you're trying to send the craft to. Yeah, so it's just their experience is, if we get this right, their experience is that now they provide an input and the aircraft actually goes to where they think it will go, right? So if we get this perfectly right, that's the experience that they have. And you can see that we don't get it perfectly right, but that we end up having a much more seamless experience for them that enables them to actually succeed at the task much more often. Yeah.
Did you have to add anything in to avoid fail states? Like in the last example, it comes very close to the ground outside and flipping over, but eventually it recorrects, because is it only optimizing for the goal, or is it also saying oh, we shouldn't go, if I go any more left, I'm going to flip over and crash?
Good question. It's not even optimizing for the goal. Literally all it's doing, it's taking the human controls, which end up being whatever they are at the point where you're almost crashing, and mapping that through this, forward dynamics, learned inverse dynamics of the real world. Yeah. And so, of course, you can do more clever things here. You can actually start inferring the reward function, which is also something that we've done, and start actively assisting them, right? So the notion here is that now I have no longer noisy rationality, but I have this broader kind of rationality, which is they're going to be noisy rational, but not under the real dynamics necessarily, but under some internal dynamics model that they have. So I allow people to sort of deviate from noisy rationality and listen this way. And now I can actually do more accurate reward inference because I have a more accurate model of how they're producing their actions conditioned on the state of the world. Yeah.
It is still making an assumption about the computational models being the same between the humans and the machines, right? Because humans could also optimize the reward function myopically, and there could be computational differences. Is it also something that could be considered in the future?
Yeah, so this was one particular way in which robots are not rational. We sort of taken this recipe and applied it in a bunch more ways. Robots are also not rational, so it's when they don't know the dynamics. The myopic thing is when they can't plan far enough ahead, so you can actually put their time horizon as a parameter that you're doing inference over and make that a little bit more flexible. Sometimes robots need to be risk averse, right? So they don't actually necessarily plan an expectation. They are risk averse. They plan under some notion of worst case or close to worst case. An interesting one that we looked at is humans are sometimes suboptimal because they're actually still learning what they want. So they're suboptimal with respect to what they actually want because they don't know it yet, right? And so you have to account for the exploration and the learning that they're doing when you're actually interpreting their action. So yeah, to answer your question, we've looked at more than just the dynamics model. And in fact, it's in a sense, it sounds very silly because we're still treating people as robots, but we're saying, look, there are ways in which robots have a hard time with this, and we can use some of those insight and bring them in to actually make this more flexible notion of inductive bias. The flip side is, of course, that sometimes people are better than robots are. So the flip side is to look at situations when people end up outperforming rational robots. And here's what I mean by that. Here's a situation where I have an autonomous car in the middle lane, and it needs to merge into the left lane, and there's all these cars coming. There's not a big enough gap in traffic. So a rational robot, at least according to this notions that we have today, and this comes back to a question that one of you had about what if the robot is acting in the world, how does that affect things? So a rational robot of today tends to make predictions about how, much like our quad rotor, tends to make predictions about how these cars will move and make sure that avoids collisions with them. And so that means that you can't actually merge into the left lane, so you either keep going or stop and annoy a bunch of people. That's what the rational solution looks like. And the challenge here is that sometimes these predictions are like self-fulfilling prophecies. You assume that people will keep going, you react to that, and lo and behold, people keep going. Somehow, by magic, people seem to figure this out. People magically create the space that is not there. And the reason they can do that is because they actually reason about the ways that they can influence each other's actions. And so with vanilla noisy rationality, we're making predictions about the person as if they're acting in isolation. But in reality, people are reasoning about the robot too. People are making predictions about what the robot will do. And that, the implication is very important. The implication is that the robot's actions end up influencing the actions that people take. And it's important for the robot to reason about this in order to actually navigate in human environments, as opposed to stay away from everyone. It gets more complicated, though. It's really turtles all the way, because people also think about the fact that the robot reasons about them. And the implication there is also important, which is that people know that their actions influence the actions that the robot is taking. And so really, this mutual influence is really important. So let's think about this in the context of self-driving cars. The first part, the part that is about how robot actions influence human actions, that's what enables the robot to know that if it merges in front of the person is likely to slow down because they can see that coming and they want to also avoid collisions. So that's what that gives us. The second part, what does this second part gives us? That the human knows their actions influence the robots. What this gives us is now the robot knows that in some cases it will try to merge in front of the person, then the person might actually accelerate to get the robot to go back to its lane. And this actually happens. This is not all the time, but this is something that robots have to also watch out for if they go down the rabbit hole of actually trying to change these predictions, not just taking them for granted. And so this is actually real life, because I have to confess I live in San Francisco. And it's the plethora of autonomous driving companies testing left and right. And so about once a month, I say, maybe not more often, but about once a month, I'll pull up at a four-way stop shortly after an autonomous car. And what I do is I just go. This is on video, shoot. What I do is I go because I know that the car will sit there and wait for me. And so this is something, and I've talked to the company and they thank me for the valuable data and we're friends, but this is something that you can expect people to do. So the bottom line is that noisy rationality, the way we've defined it, doesn't quite hold, because really what we have is the robot, one agent with its utility, the human, another agent with their own utility. That's how we formalized intent. And the two utilities don't have to be identical. They are when you have a human-robot team that are collaborating, but when you're sharing the road, you each care about your own goal, your own efficiency. Yes, you have some common terms, like you care about avoiding each other, but it's not common payoff. It's not zero-sum either, it's general sum. So if we could solve this game, if we could solve it, just to get an idea, it would look something like this. We'd start at the end of the time horizon. We would set the values to 0 for the human and the robot. We'd go back in time for every state. We'd look at all possible actions that the robot could take. For each action that induces a probability distribution using rationality of what the human might do. We can use this now to update the robot's Q-value function to figure out what the robot's optimal action is and update the robot's value function. So the robot is deciding what action to take such that when the person responds, that works out well. And then that then updates the human's value function. And then we do this for all states, and we propagate this all back in time. But I can't do this for real robots, right? Not in continuous state and action spaces. This is a no-go. And so one thing that we've been experimenting with is this hierarchical decomposition. We do solve the game, but we solve it at what we call a strategic level, where we simplify state and action and dynamics. And we actually do this offline and compute the values for the human and the robot. And then online, we have a tactical level that does model predictive control, continuous state and action spaces, but uses the value from the strategic level as a heuristic. So that's been our sort of most successful approach so far of all the things that we've experimented with. So at the strategic level, we do this crazy thing, but we do it for a simplified state action space. The tactical level, so the vanilla version of what we do, and I simplified it here to be deterministic just because the equations are nicer and it's computationally cheaper. So we would be predicting a human trajectory that maximizes the human's utility, and we'd be giving that to the robot. So that's sort of the vanilla approach, predict what people want to do, give that to the robot, have the robot optimize its own utility using that prediction. Now, at the tactical level, we're a little fancier than that, even there, because we want to capture the fact that the robot can actually influence what the human is doing. And so we actually make UH a function of UR. We say the model the person is optimizing their utility. That depends on their trajectory, but it also depends on what the robot decides to do. And now the robot is facing this nested optimization problem where it's wondering, what should I do? Such that when I expose the person to that and they optimize their utility, that ends up working the best for me. So this is, and we do model predictive control here, so we take a first step. We really do this. We solve this using, we've experimented with a few things. Maybe one of the most successful one was a quasi-Newton method. And the one trick here is that we also add a terminal cost. So we do this for a short time horizon, and then it's guided by the values that we get from the strategic level, the thing that we solved offline. So let me share a little bit of what happens. So this is, by the way, the robot's value that you see. The robot comes here. And what it expects to happen is that the person can actually move out of the way so that the robot can continue. This is one interesting result here. Now, people don't always do this. So when they don't, so this was a human driving, who didn't actually move out of the way. And what you see happen here is that you'll see more and more blue region there that attracts the robot onto the right lane so that it overtakes. So we can deal with that too. A really nice example I found is this one. Here the robot accelerates to try to get in front of the person slows down to make space. Here, I'm going to play this again. Let me see. Okay, so here's the robot accelerating. Here, the robot goes. The person accelerates to deter the robot. And then the robot has to slow down and go behind. And so I'm excited because we're starting to see actual mutual influence come out of this, and robots that are able not to just be there paralyzed, but are able to try to influence, but also be responsive to, if it doesn't work, it doesn't work, and I can do something else. And so we've taken, again, noisy rationality, and by thinking about where people are actually better than robots, it's really that the interaction is game theoretic and people get that. And so we've broadened it to be now game theoretic rationality. And we've done more and more things, and we could go on to this notion of very flexible assumptions about rationality, where we still use the notion that people have intent, but we try to use that in as flexible of a way as possible. Yes, question.
In contentious situations like this, people also try to resolve the uncertainty as much as possible by kind of waving at each other, sort of making eye contact and so on. So with robots, it's kind of difficult to see how they would do it with humans, vice versa. Have you thought about, exploring that possibility? Again, I just have no idea how you would do it with.
Yeah, it's an interesting question. I stay away from gestures because, for me personally in my research, because they're highly kind of cultural dependent and change a lot. But what a lot of our work has been is body language that emerges as a consequence of formulating the problem in the right way and optimizing for the right thing. And so we see some of these strategies, like the ones that we've just seen, where the robot sort of goes and expects the person to slow down. We've also had things emerge like a robot inching forward at an intersection to probe the person and see if the person is slowing down and letting them go or not, right? And so it's not that we have reasoned explicitly about what the person is inferring about the robot. It's just that we know that there are different kinds of drivers out there, and we maintain a belief over what that is, and we take information gathering actions to resolve ambiguity. And so that results in non-gesture per se communication, but communication through the actual physical actions that you can take. Mm-hmm. So this has been sort of part of my journey, I'd say, to try to push the boundaries of what we can do, starting from this very simple starting point, right? People optimize for utility, going towards broadening that more and more. Now, one last aspect that I am very excited about these days is the fact that we're never going to be exactly right. We're never going to have this space that's not super huge, but somehow manages to capture every human behavior that we might encounter. That's just, it feels hopeless. And so what do you do then? How do you make sure that your robot still works in spite of that, in spite of completely having misspecified the space that you're actually doing search over? And so here's an example that you actually saw in the beginning. What we did here is we spilled some coffee on the floor. Now Sylvia is avoiding the coffee. The robot models Sylvia as noisy rational. The robot has no idea that there's coffee on the floor, that humans might care about avoiding coffee that's spilled on the floor. And so Sylvia is kind of deviating, but the robot very stubbornly believes at every point that Sylvia will turn around and start going straight towards her goal, because that's its hypothesis space, right? So what do you do about that? Well, what we'd like to do is, at the very least, I don't know how to fix this, right? I don't know how to invent the concept of coffee, at least not without interaction from the person. So I don't know how to fix this. But I think at the very least, we should be able to detect that we have the wrong space here, right? That to detect that we can't actually explain what's going on with the hypothesis space that we have. In other words, I'd like for robots to be aware that there's always going to be a potential reality gap between the model and how the actual human works. And so I'd want the robot to be minding this gap, to be actively monitoring for this, so that at least it figures out that something is going on that it doesn't know about. And that's been something that's been really exciting for me lately. And it went back it's for the first time in my life a story where some hack that we had to tune ended up being the thing that we could actually do in a principled way, and it's the answer to this problem. So in noisy rationality, real quick, I haven't talked about this, but we stick a parameter beta in there. It controls, always. We do it because it captures our assumption about how noisy, how suboptimal we think the person will be. If I said, so real quick quiz for you, if I said beta equals 0, what happens? What am I assuming about the person? Yeah, we have a uniform distribution, right? If I said beta closer to infinity, then I'm modeling a person who's perfectly rational. So, what do? We tune this beta. We start with 1, right? And we make sure that the inference kind of works well enough. That's what we do. The key thing here was to realize that this beta, not only can you actually make it part of the inference so that you don't have to tune it yourself, but making it part of the inference is what's going to tell you whether you're misspecified or not. Because basically, as you actually allow the robot to be doing inference not just over the possible intents, but also about how rational essentially the person appears for those intents, you end up being able to capture that you essentially can't explain what is happening. You end up, essentially, you're going to fit a model. The human's going to appear irrational, right, under all of the hypotheses that you have. The only way you can get that probability distribution to go up is by making beta close to 0. And that should tell you that you don't know what's going on. Because if the person is very irrational, according to any hypothesis you have, then either the person is broken or the model is broken, right? And so it's pretty safe to assume in this day and age that you don't have the right model. So that's what we do, right? So here we're going around, we're making predictions. When the person does something that we can't explain, the robot is going to use that as evidence about beta. Beta is going to go low. And what I really love about this is not only that now we have a flag that says, I don't know what's going on, but at the next time step, we don't have to do anything special. We don't have to if statement it, we don't have to switch case it, because just by using the posterior that we have over beta, which now puts a lot of probability mass on low betas, what's going to happen is we now are going to have higher variance predictions. The robot is going to be more uncertain about what's going to happen with the human in the next time steps. That's what happens when you have a lower beta. It results in distributions that look more and more uniform. So here it is in practice. So if you fix beta to some high-ish thing, which is what we usually do, you see this go on. And the person goes to one goal, the person goes to another goal, and everything's fine. But in a second, the person is going to start going towards a third unmodeled goal. And the robot is going to think that any moment the person is going to turn around and go towards one of the goals that it actually knows about. So that doesn't work. The other thing you could do is always keep a low beta, but then you're always very confused about what the person will do, so that's not good either. And so by inferring beta, we're starting to get the best of both worlds. We're starting to see that, so here's the coffee example. We're pretty convinced. Now Sylvia is deviating, and all of a sudden, our entropy increases here in our predictions. And now when she's starting to be aligned to the goal again, we start trusting the model again. With the goals too, you go towards one, you go towards the other. The robot says, OK, this model makes sense. The moment Sylvia starts going towards the next goal, now this doesn't make any sense anymore, and the robot is confused. And here it is in real life. I'm going to try to do this. Let's see. Nope, it doesn't work. It's OK. We can skip that. One worry of mine is how to handle multiple people. This whole talk has been about one robot and one person. In reality, we have multiple robots and multiple people. And what's hard about multiple people is that not only does each of them interact with the robot, but they also interact with each other. And it's really it starts getting hard to capture all this complex interactions, mutual interactions. And so one thing that we can do is actually treat each person as being independent. When they're actually independent, everything's okay. When they actually start interacting, then beta's going to go down. The robot's going to realize that its predictions don't make any sense. They're not consistent with what's actually happening. And it's going to become more uncertain about what the people will do in the next time step. So here are Jaime and Sylvia and two little quad rotors. And they're moving along and everything's fine, but now they start actually interacting. The robots get confused. That quad rotor actually paused and stayed behind and to allow the situation to resolve. So I like seeing that. And then finally, when it comes to pushing on the robot. So when I push on the robot and my corrections actually is about something that is in its hypothesis space. So I push it closer to the table, and it's actually reasoning about distances to objects like the table, so it can actually make sense of my correction. What we see is that it updates its estimate of what I want. It also estimates rationality, which, like I was saying, only starts at 1 and goes up because it can actually make sense of my correction. When I push it and I push it to correct it about something that it doesn't actually know how to reason about, then what happens is very quickly it realizes that it doesn't know, that it can't make sense of my correction. And what that leads to is the robot tends to stick more to its prior and not actually update. Which but I want to just point out, this does not actually fix the model, right? This does not have the robot magically figure out, oh, the person must be avoiding the coffee, oh, the person must be caring about this or that. I still don't know how to do that. But now what happens is at the very least it enables the robot to know that it doesn't know what's going on, as opposed to sort of blindly keep on focusing on the hypothesis space that it has. Okay, so I've been asking myself what the right inductive bias is when it comes to human-robot interaction. To me, somehow we have to be using some form of people have intent, but the exact right way to do that seems to be tricky. And to me, it's been sort of a two-pronged approach. On the one hand, take the models that we have and fix them, incorporate more and more information so that they're better, that they're more flexible. On the other hand, make sure that we can still do reasonable things when we're still wrong, where our assumptions don't actually hold. In general, a lot of what I do is giving robots these models of people as doing some form of optimization, or we didn't get a chance to talk about it today, but some form of Bayesian inference about inferring things about the world, inferring things about the robot. And I think those two tools have been, at least for me, really useful, not because they're correct, not because that's what's actually happening in people's heads, but because they seem to be useful. They seem to get us to have robots that know how to coordinate with us, that know how to collaborate with us and get better at doing what we want, with low sample complexity and with pretty good robustness to things like covariate shift. So with that, I'd like to thank you and thank all of my students and faculty collaborators at Berkeley, and we can discuss some more. Thank you.
What are your thoughts on, you talked about making the human look like a robot, but what about making, reversing that and making the robot more like a human and using these models to say, I want to restrict the space of hypothesis for my policies?
So what if we incentivize the robot to, in essence, be closer to a human-like policy and when it's searching for its own policy? So I think that, first of all, that idea makes a lot of sense in something like imitation learning, right? Where you collect a lot of data of how people act, and you don't want the robot, don't want to bother with, oh, there's some objective function, I'm going to optimize it, but you just want to copy the human behavior, but in a way that generalizes. And so there you have the same question of how can I actually restrict my space of policies that I'm searching over for myself to be so that I avoid the same sort of issues like distributional shift. So that's one answer. The other answer is, in general, I have not been a proponent of making robots be natural just for the sake of having them be natural. A lot of the times you see that these strategies emerge, like inching forward into an intersection or nudging towards someone's lane and seeing how they react. And they're natural looking strategies, but I think it's important that they emerge out of having formulated the problem correctly, having a good objective function, or at least distribution over objective functions for the robot to optimize, enabling the robot to reason properly about people, and figuring out what the right thing to do is. And if the right thing to do is to act in a human-like way, then great. Sometimes we found that that's not the right thing to do. So we have this crazy example of a car that is actually polite and cares about your efficiency, not just its efficiency. And what it does at a four-way stop is it actually starts inching backwards. It inches backwards to get you to go faster through the intersection. And I kid you not, as crazy as it sounds, in user studies, this isn't simulation in a driving simulator, but with real people, it actually works. People go faster through the intersection. It's a strategy that actually, what do you do? When you have people behind and all of that, it gets more complicated. But my point is, it's not something that humans do, but that doesn't mean it's not something that we can interpret easily and respond to in the way that the robot intends. So I think for me, that's the goal. It's to get the interaction right with whatever tools it takes. If naturalness is part of that, then I'm very happy for naturalness to be there. Yeah.
Maybe this is sort of wrapped up in sort of the nested problem that you had. But at the end, you talked about how the robots can determine when they have no idea what's going on, when their hypothesis seems to be incorrect. Can the agents also reason about people and whether people are confused about what the robot's going to do?
Somewhat. So that's really interesting. I think that you can have these different models of how people might be responding to the robot, and the same trick applies. If none of the models seem to fit, then you know that probably you don't have it right. Yeah.
Clarification question on the beta learning. I'm trying to understand, that must be a prior or something else, because how else could I tell the difference between beta being small but the actual utilities were large, because the dopamine in my head gives me like 10 units of utility, versus beta being large but the actual scale of the utilities are smaller, and like nothing in the behavior data that I collect could ever tell these two explanations apart.
No, it's true. You have to commit to a particular scale on your utility functions, and within that, you can actually start comparing the inferred beta. And you have a joint distribution over beta and theta. In practice, what we do is, for instance, we use linear combinations of features, and we use the unit sphere, right? So we use unit norm vectors, and then we don't have that problem. Or we have this discrete theta as goal 1 or goal 2, and then we don't experience that. But yes, in general, you have to be careful about this. In a sense, it's a blessing and a curse of the Boltzmann distribution, right? It's what enables you to do things like infer the level of rationality, but it's also a pain in the butt from the perspective of actually being careful about that scale. Yeah, it's a good observation. Yeah.
Two kind of related questions. On the example with the cars merging, where you said like humans do better, one question is, there have been things you're aware of where like the robot, like you have two robots communicating with each other, kind of like I have this model and you have this model, or I'm going to anticipate or give you a heads up, where you couldn't do that with necessarily a human. That's all like in the back end. And the other thing is with that model, like the ultimate goal a lot of times is like, oh, I have to make an exit here and I'm like late, right? And so like the human doing that will make a non-intuitive move, not because it wants to merge, but because it's like if it doesn't merge, it's not going to get to the end goals. How do you model those like second objectives where it's like I need to make this happen because then like if I don't make this happen, the next thing is that the like not knowing enough into the future example you were saying where the robots might not have perfect information?
Okay, so for the first one, robot. A lot of what we've talked about can certainly be applicable to situations where you have robot-robot, but there's no explicit communication. The advantage that we have with robot-robot is that in some cases, maybe we actually agree on a protocol and we can actually coordinate wirelessly in ways that we can't do that with humans because we can't beam stuff to their brains. That said, I don't want to really claim, I mean, our focus in the lab has really been to stick to our problem is coordinating with humans, which are these entities that we don't have any kind of explicit control over. It does apply to robot in situations where robots are actually doing things like optimization. But if they're running an RT or something like that, and you try to use our cranks to make inferences about what the other robot is doing, it doesn't work at all. Your second question, I'm trying to parse out a little bit. So when it comes to situations where I'm doing X because that sets me in a good position to do Y, you're absolutely right that a challenge with model predictive control when you plan for short time horizons is that you're going to miss out on those things. It's even simpler than that. We couldn't get our robot to either predict or do an overtake because it never gets the carrot at the end, which is, I can actually get back into my lane. And that's what's one benefit of having this hierarchical structure where we use the value, we actually solve the game and we use the value as a heuristic, is that you're even though at a simplified level, even though that's simplified, you can still actually get a lot of information about long-term behavior, strategic behavior out of that. So that's one benefit. The main benefit is that we actually have, which is a little subtle point I didn't get a chance to talk about, is that we actually have the correct information structure in the game. In other words, at the tactical level, remember we were giving the human access to the robot's trajectory. And so that makes this assumption, that's a static Stackelberg game instead of a dynamic game. It makes the assumption that the person can just magically see what the robot plans on doing. And we'll take that for granted and not try to influence it, but just do a best response to that. That's okay for the tactical level. The strategic level is really nice to have to capture the actual mutual influence and the fact that people can't magically see what the robot plans to do and vice versa. And so that, I think, is the really main benefit, but a side benefit is definitely that we can actually get information about longer term. Yeah.
I actually really found it inspiring to think of humans as not just intent-aware, not just irrational, but I'm curious, when all our policies are not explaining the human behavior data all that well under these models, I can imagine maybe the black box policy fitting approach, maybe it's ending up fitting things better, but who knows whether it's robust or covariate shifts or things like that. So I'm curious about what is the get the best of both worlds, basically.
It's definitely something that we're working on and wondering ourselves. You can imagine very simple things where you do this beta inference trick, right? And so you default on your simple model, but when it's not doing a good job, you then go to your black box model. You can imagine more complicated things like training a black box model in simulation using the simple model as your simulator. So you can start doing domain randomization. You can start doing all sorts of crazy things that are basically treating noisy rationality or broader noisy rationality, whatever it is, as your simulation, essentially, that you practice in before you go off to real world. And that can help you with some domain randomization, perhaps actually avoid things like covariate shift. I don't know. All in progress, or at least not even in progress, but more like in the plans for someone to start working on. The summer is coming. We'll have more time. Any other thoughts, comments? Yes.
How are these algorithms different from something that would be used in multi-agent systems?
Yeah, so that's the question of robot-robot versus human-robot. With robot-robot, a lot of times you have explicit communication, or you execute in a decentralized way, but you plan in a centralized way. With humans, we're kind of stuck with whatever humans are. We can influence human behavior. We can make people adapt. It takes some time. We have to familiarize them. So that's sort of the challenge of working with the human setting as opposed to another robot. Now that said, you can imagine that similar things could be done on the robot level if you have absolutely no communication, but it depends a lot on what you can or can't assume about the other robot. Yeah.
So I was wondering if you could give us a sense of when you go through these sort of increasingly complex models of human behavior, how do the required sort of sample complexities of the agent change? Because you can't crank up a simulator, so I'm assuming you have to be particularly careful about these things.
Yeah, so in the days where we were just doing noisy rationality over, which of these three goals is it? Those were great days. And we sort of scaled up to here are a few features on the order of 10. And then Bayesian inference stopped working explicitly, so we had to do sampling, or we had to do things like maximum likelihood estimation, and we had to do it online, which was really tricky. So more approximations were involved. Now, as we start adding in the time horizon and the parameters of the dynamics and all of that, not only do we get into sample complexity issues, though nowhere near just having a high capacity neural net policy. So we're still babies compared to that world. But we get into sample complexity issues. The more fundamental thing that we're getting into is that having a belief is really important because there's multiple possibilities explaining the behavior that you see. There's inherent ambiguity between the reward function and the dynamics. There's inherent ambiguity between the way, other kinds of biases that the person has when they're actually doing the planning, what those are. And in an extreme, if you make that, we've also played with making that very flexible. So we've played with reward comes in, there's a neural net that does the planning. So something like value iteration networks or something like that. And then we learned the planner that the person is using, right? Just to see if that would ever be feasible. And there you have to be very careful about how you regularize that, what sort of prior you can actually impose, because you can take a reward and have a perfect maximizer. You can have the opposite reward and have a perfect minimizer, and they're going to explain your data just as well. And if you need to figure out if it's important for the robot not to make predictions about the person, but to figure out what the person wants so that it can help, it's really important to get the sign of the reward function correct. So I think, priors there end up being really important, and sample complexity is an issue. And then computation is also an issue. And we're starting to get more and more into that. Yeah.
So I totally am with you that when humans and robots start interacting, this communication of intent is going to be sort of central to having fruitful interactions between the two. And I think we've seen that ways to indicate intent, such as like turn signals on cars, can be vastly helpful in allowing humans to interact with each other. So I was curious about your thoughts about whether we should be also looking into maybe mechanisms like lights or ways we can signal to the robot what our intent is in general cases, so that the robot doesn't need to reason about what we might be wanting to do, versus, so development of better signals for communicating intent back and forth between humans and robots versus rationality.
Yeah, absolutely. I think that's a really interesting and important area. On the very practical side, I'll say that lights and sounds and that kind of communication can work really well if it's depending on the particular thing that you're trying to convey. Sometimes we find that motion is very intuitive to read into and does a better job disambiguating. Sometimes we found that motion is very confusing and needs to be augmented by these other channels. So on the practical side, all I'll say is it's very worthwhile to invest in that, and we just have to make sure that the physical actions themselves end up being consistent with what it is that we're trying to communicate with these other channels. So that's one thing. On the sort of less practical side, I'll say that when we write out these this framework that I was talking about in the beginning, where we can take all sorts of human behavior and interpret it as evidence about what's going on. I think things like turn signals and so on also fit into that story. That whatever information people can provide, we've gone as far as if the person writes down a reward function, right? So it's a very explicit sort of, here, have it. Of course, natural language plays a role into this as well. We just have to be careful to interpret these things in a flexible way, because people say or indicate things that they think they want, but that they don't actually want. And I don't, I think that the key there is to have uncertainty and flexibility over what's going on, and be able to make sort of follow-up queries and be nuanced about the way we're interpreting these behaviors, so that, for instance, if the person is still learning about what they want and they're sort of saying, oh, I want this and that, you can't really actually trust this yet, because they haven't been exposed to all the different options for them to actually realize what it is that they care about. So there's nuance there too. So that's a much more philosophical thing, but we have to be careful about what people directly indicate versus what it is that they actually want. All right. I think that's a wrap. Thank you, everyone, for coming.